Hello and welcome. If you're here for some GCSE chemistry revision, you've come to exactly the right place. Today, we're going to get you totally exam ready for AQA section 4.6.2, which is all about reversible reactions and the really cool world of equilibrium. Let's get into it. So think about most of the reactions you've learned about. They're pretty much a one-way street, right? Reactants become products, and that's the end of the road. But what if it wasn't? What if those products could actually turn back into the very things that made them? Well, that's the whole idea behind a reversible reaction, and it's what we're tackling today.
All right, here's our game plan. First, we'll nail down exactly what these backward reactions are. Then we'll look at the balancing act they perform, which is called equilibrium. And for all of you on the higher tier paper, we'll dive into the master rule, Le Chatelier's principle, and how you can use it to basically control these reactions.
Okay, let's start at the very beginning. What on earth does it mean for a reaction to be reversible?
So here's the core definition you need. A reversible reaction is one where the products can actually react with each other to remake the original reactants. And because of this, we can't use a normal arrow. Instead, we use this special double-headed arrow symbol. It's a huge clue that the reaction is a two-way street. The forward reaction goes left to right, and the reverse reaction is happening at the same time, going right to left.
So, if you've got reactions happening in both directions at once, you might be wondering, what happens? Do they just keep going forever? Well, not exactly. If you put them in what's called a closed system, which just means you've put a lid on it so nothing can get in or out, they eventually reach this amazing point of balance. And that point of balance is called dynamic equilibrium. Now, the word dynamic here is super important. It does not mean the reactions have stopped. No way. They're still whizzing along. It just means that the speed, or the rate, of the forward reaction is now exactly the same as the rate of the reverse reaction. And because they're perfectly balanced, the total amounts of reactants and products don't change anymore. They're constant. Here's a great way to think about it. Imagine you're in a shop with two floors. There's an escalator going up and an escalator going down. If, say, 10 people are going up every minute and 10 people are coming down every minute, the total number of shoppers on each floor stays the same, doesn't it? People are still moving, it's dynamic, but the overall numbers are balanced. That's equilibrium.
Now, let's quickly talk about energy. This is a key rule to remember. In a reversible reaction, if the forward direction is exothermic, meaning it gives out heat, then the reverse reaction has to be endothermic. It has to take in that exact same amount of energy. It's a perfect energy trade-off. Okay, higher tier students, listen up. This next part is specifically for you. We're getting into what I like to call the master rule of equilibrium. It's called Le Chatelier's principle. And trust me, once you get this, you can predict exactly what's going to happen when we start messing with the conditions. So, Le Chatelier's principle says this: if you have a system at equilibrium and you make a change, the system will respond to counteract that change. That one word, counteract, is everything. You need to burn it into your brain. Whatever you do to the reaction, it's going to shift its balance to try and oppose you. It's always trying to get things back to the way they were. Let me make that even simpler. The reaction just does the opposite of whatever you did to it. That's it. If you heat it up, it's going to try and cool itself down. If you increase the pressure, it's going to try and take up less space. Just remember, do the opposite, and you'll be able to figure out any of these problems. So why is this principle so useful? Well, if we know that the system will always try to fight back against what we do, that means we're in control. We can become the puppet masters. We can deliberately change things to force the equilibrium to shift in the direction we want, which usually means making more of the stuff we're trying to sell. And for your exam, there are three main levers you can pull to manipulate equilibrium. We can change the concentration, we can change the temperature, and, only for reactions with gases, we can change the pressure. Let's go through them one by one. First up, concentration. What happens if we suddenly dump in a load more reactants? Or what if we find a way to remove the product as soon as it's made? How is the system going to try and counteract that? Well, according to our do the opposite rule, if you add more reactants, the system kind of panics and says, whoa, there's way too much of this stuff. To counteract that, it tries to use it up. And how does it do that? By shifting the equilibrium to the right to make more product. Same idea if you remove a product. The system will try to replace what's missing, again, by shifting to the right. Okay, lever number 2, temperature. Remember that slide about exothermic and endothermic reactions? That's the key to this whole thing. The system is always going to try to oppose whatever temperature change you make.
So if you increase the temperature, if you heat things up, the system will try to cool itself down. It does this by favoring the endothermic reaction, because that's the one that takes in heat. And if you decrease the temperature, the system tries to warm itself up by favoring the exothermic reaction, the one that gives out heat. See? It always does the opposite. And finally, we have pressure. Now, this is a massive exam tip, so listen carefully. This rule only, and I mean only, applies to reactions that involve gases. If you have a reaction with just solids or liquids, pressure does absolutely nothing. So, how do you figure this one out? It's easy. You just look at the balanced equation and count the number of gas molecules on the left side and then on the right side. If you increase the pressure, you're squashing everything into a smaller space. So the system will try to reduce that pressure by shifting to whichever side has fewer gas molecules. And if you decrease the pressure, it'll do the opposite and shift to the side with more gas molecules to try and fill that space.
And there you have it. This is your higher-tier cheat sheet for the exam. To get more product, you can increase the concentration of reactants. For temperature, you need to know if you want the exothermic or endothermic direction. And for pressure, just count the gas molecules and remember that high pressure favors the side with fewer moles. If you can master these 3 points, you are going to smash these questions.
So we've gone through all the theory, but this is why it really matters. By applying Le Chatelier's principle, chemists can control these reactions to get the maximum possible amount of product. Think about making ammonia for fertilizers, a process that feeds billions of people. Chemists use these exact rules, tweaking the temperature and pressure to get the best possible yield. So these aren't just rules for an exam. They are literally the tools that help shape our modern world. Pretty cool, huh?